In recent years, there's been a lot of progress in estimating hand pose and shape. In this paper, we go beyond this kind of estimation and propose a new task where, given a single RGB image of an object, we want to predict how a human would grasp it. In practice, we want to predict multiple solutions for each object which tackle different grasp affordances. This task is considerably more challenging than similar work on robotic grasping, where there are usually many less degrees of freedom than with the human hand. However, by using the hand, we can leverage work on human hand modelling and grasp taxonomies, and the human hand can be transferred to robot manipulators or used for learning from demonstrations. It's also relevant for virtual and augmented reality applications. To increase the accuracy of the grasp predictions, we also estimate the 3D geometry of the scene. We observe that there's no existing dataset that contains realistic grasps on a variety of both grasp types and objects. So, we created the YCB-Affordance Dataset, with manually annotated grasps for all objects on the YCB object set. These are common objects that are important for robotic grasping and manipulation tasks. We use the GraspIt simulator to semi-automatically annotate the position and pose of the hand, and annotate several grasps per object, according to the most common ways we, as humans, usually grasp them. We also annotate the grasp type according to the grasp taxonomy of Fej and colleagues. Grasp annotations are extended using the symmetry of the objects. We then use the YCB video dataset, which contains real videos with multiple objects and ground truth pose annotations to place the grasps in the scene. This dataset contains challenging scenes with occlusions and a huge diversity in object poses for which we want to estimate the grasps. Finally, we remove those grasps that would intersect with other objects or with the table plane. The YCB-Affordance dataset contains more than 28 million realistic grasps on everyday objects based on real images. We then design a generative model that predicts a distribution of possible grasps for each object from a single RGB frame. We do this by first reconstructing the 3D layout of the scene, for which we use state-of-the-art pose estimation or object reconstruction. Pose estimation is used when the objects were seen at training time, such as those in the YCB-Affordance dataset, and we use object 3D reconstruction for new objects. When there's more than one object in the scene, we concatenate the mask from the target object as a new channel to the input image, which allows us to run the model for multiple objects. We then extract features from the input image and predict the most suitable grasp type for grasping such an object. We sample a random grasp orientation that makes the model stochastic, and an MLP refines the orientation and the hand pose that best suits the object's surface. We use a differentiable Mano model to regress a fully articulated hand mesh, and a discriminator on the Mano parameters to ensure that the hand pose is anthropomorphic. The model is also trained by minimizing the hand-object mesh interpenetration, the distance between the fingertips and the surface of the object, and cross-entropy on the grasp category is predicted. After this pipeline, we combine the information of the two branches of the model and align the predicted hand mesh with the object mesh surface. In a final post-processing step, we follow the kinematic chain of the hand to bend or flex each finger. This minimizes hand-object interpenetration and maximizes the stability of the grasped object. These experiments show the effect of this final optimization with predicted grasps on ground truth objects. The first evaluation is done on the OBMAN dataset made with single and synthetic objects from ShapeNet. We then evaluate on the YCB-Affordance dataset. In this case, the objects had been observed in the training time, so we show the results from the pose estimation pipeline and our grasp estimations. Since the model is stochastic, we run the forward pass multiple times for objects to obtain a distribution of grasps. And for simplicity, here we just show the one with the highest grasp metric with no interpenetration with other objects. The model is shown to be robust to occlusions and challenging poses. The main sources of errors are due to wrongly detected objects or inaccuracies on object pose estimation. For instance, in this case, you can see the picture model is misaligned with the ground truth and the hand mesh intersects with the hand grip. All the code used for training, the data, and a pre-trained model will be made available from the project website.